Good morning, everyone. Thank you very much for attending. I think we're going to get started here. So today we're going to be talking about our experiment tracking the 2024 solar eclipse using DARWin dual software. So my name is Mackenzie Woodman. I'm the remote sensing application specialist here at Spectral Evolution. So Spectral Evolution has been around since established in 2004. So they've been around for about 20 years now. And we are the leading manufacturer in high quality, full range spectrometers, field spectrometers, and spectroradiometers. We're also located in Haverhill, Massachusetts, so the Boston area, and we're made in America. So our spectrometers and spectroradiometers have a very diverse set of applications that's rapidly expanding with research. So there's many applications in hyperspectral data acquisition, remote sensing and vegetation, mining and geology, and photonics and calibration transfer. So with remote sensing and vegetation, this can be various different environmental studies, species identification, water quality, and things like that, as well as in the mining sphere, there's rock identification and mineral identification, as well as vectoring for resources. And then with photonics and calibration transfer, we're very frequently used for calibration transfer for satellites, remote sensing satellites, as well as drones. So today, this experiment was conducted using the Naturaspec. This is our most popular instrument. It's a full range spectroradiometer, which spectroradiometer means it has a radiometric calibration. This allows it to do direct energy measurements using various different accessories, as well as just the instrument itself. It has a very high resolution, and it has the highest sensitivity of a field spectroradiometer on the market. So its resolution is 2.7 at 700 nanometers, 5.5 at 1500 nanometers, and 5.8 at 2100 nanometers. So today I'll start out by just giving you a couple fun facts and introducing the 2024 solar eclipse. So this total eclipse is when the moon completely blocks the sun and creates light that's typical of dawn or dusk. So not complete night, but it shades an area. These things have been fascinated about throughout human history. The oldest recorded total solar eclipse was in 1375 BC or 1223 BC. Throughout history, these are, when it gets that far back, these get a little hard to determine what year, but because we can project where the sun and the moon's position was through history, we're able to actually date different historical events using the recording of a solar eclipse. So it helps with dating of historical events when it gets that far back. This solar eclipse was pretty unique, as its path of totality crossed parts of 4 states in Mexico, 15 US states, and 5 Canadian provinces. And we won't see another full solar eclipse like this until the year 2044, and it will be in a very different location in North America. Although total eclipses happen on Earth about every 18 months, they will not occur in the same place for 360 to 400 years. So don't expect to see another solar eclipse in this location in your lifetime. So what we've conducted is irradiance measurements using a few of our different accessories and 2 different Naturaspecs. So we were able to use the Naturaspec simultaneously to measure global horizontal irradiance and direct normal radiation, and then calculate the diffuse horizontal radiation. So this is the equation to do that. So global horizontal irradiance is the total radiance on a horizontal surface. The diffuse would be everything that isn't directly coming from the sun. So the light that's bouncing around the atmosphere or off of other objects that end up hitting a horizontal surface. So you can think of that as a shaded surface. So anything that's, if you think of it like a shadow, it's not complete darkness. You can still see it, and that's because there's diffuse radiation there, or diffuse irradiance. And then direct normal radiation is the sun energy that's coming directly from the sun, so straight through the atmosphere, hitting your spectrometer. So in order to measure the global horizontal irradiance, we used an inline diffuser, which is shown in the hand on the right. This connects directly to the end of the fiber optic cable from your instrument. And this will give you a 180-degree field of view. It can also be mounted on a pistol grip, which can be mounted on a tripod, so that you can do various different experiments with a 180-degree field of view. These can be used for broad surfaces or energy measurements from light sources. There's many different applications, but in this case, we used it to measure the global horizontal irradiance. So to do that, we put it on a tripod as high as possible as to not be obstructed, and made it completely horizontal in order to measure that. Our other accessory that we used in this experiment was a Gershun tube. This is a 1-degree optic with a radiometric calibration. This is perfect for targeting small targets that are far away. So with this, it has iron sights, so we're able to train it directly onto the sun and measure the direct irradiance. These can be used in drone applications or other applications where you want to have the smallest field of view as possible. They're also perfect for measuring different light sources as well. So during this experiment, we chose the Woodsum Farm Park in Amesbury, Massachusetts. We were there we were measuring from 2:16 to 4:39. That was the total time for the solar eclipse to occur. We chose this area because it's a very large and unobstructed field of view. So we were at the top of a hill. It was a perfectly sunny day during our sampling. There was a few clouds towards the end of our sampling event, but more or less it was unobstructed through the entire time. The percent coverage for the eclipse here was not a total eclipse. We were able to collect at 94.2% coverage at totality. And we would set up the instrument so that it could take scheduled sampling every 5 minutes. And so the only thing that we needed to do was readjust the Gershun tube because the sun's path was moving across the sky. And so we would adjust that 30 seconds before each sampling. So now I'm going to go over a little bit of the DARWin Dual software. So this is how you operate 2 spectroradiometers or spectrometers in at the same time. So you're able to connect both spectrometers to your computer or tablet to in order to use them in sequence or simultaneously. So here you have in the top left instrument A. You'll connect to that COM port or Bluetooth via Bluetooth or cord. And then instrument B will be your other one. And then you can set on the right your different operation modes, which is how is the data going to be processed together for your experiment. And then you can select your measurements and file output paths the same way that you would use DARWin using a single instrument. So there's several different modes that you can collect data using DARWin Dual. So the first is the ratio white plate calibrated. This is computed by dividing processed reflectance spectra from the instrument, and the white plate reference scans are synchronized between instruments, and then it will use that for the rest of your sampling event. The direct radiometric calibration allows you to do a radiometric scan simultaneously from both instruments, and then each will be collected independently, so they won't combine the data at all. Radiometric difference would be one instrument's data is subtracted from another. So if you're using, in this case, if you want to measure diffuse solar radiance, you could subtract a Gershun tube from a diffuser. So that's exactly what we've done here with minor differences. Or you can have it calculate a ratio from one instrument to another. So this is probably the most commonly utilized dual instrument sampling mode. In this case, you could have an inline diffuser measuring your downwelling irradiance simultaneously when you're collecting reflectance measurements. So you won't have to worry about your reference data or your reference scan changing every time you take a target. So every single time you take a target scan, you're going to have it optimized to the light conditions that you're working under. And then independent, that allows you to select your different operating modes. So what kind of spectral math is one spectroradiometer doing with the other set of data? So it allows you to customize for your different applications. And so this is the view that you get. So you'll get your spectrum from instrument A on the top, and then your spectrum from instrument B on the bottom, and then whatever operation that you've decided to do. So say you're subtracting B from A, you'll get the result in the middle. And then on the left, you can do timed scans in the bottom left. You'll also collect GPS and other metadata at the same time, the same way that the normal DARWin software works. So now we can get into the actual data that we were able to collect. And so this is the irradiance from the start of the eclipse to totality. And so we have a little graphic here. So the energy will start out the highest, and then as it gets to totality, you'll see it decrease significantly. And so there you see it. At totality, the lowest amount of energy is recorded from the global horizontal irradiance. And so I'll play that again one more time. This is the full energy of the sun, and then it drops down to totality. So the results are here. On this graph on the right, you can see the global horizontal irradiance. is the blue line, the total direct irradiance is the orange line, and the diffuse irradiance is the purple line. So these represent the energy change throughout time through the eclipse. It doesn't recover entirely on the right side. This is due to the eclipse occurring towards the end of the day. So the sun is in a different part of the sky at this point, and there's less energy at that time of day. There is no significant difference in the depreciation between shortwave and longwave. It appears to be blocked uniformly. We may have seen a different disparity if we were at totality or 100% coverage, but we weren't able to observe any of that in this experiment. But all three of these lines approach zero towards totality, and so that is to be expected that we had the least amount of energy at totality compared to every other sampling. So that's consistent with what should be observed. But it doesn't reach entirely zero at any of these points. This is due to there always being some amount of diffuse irradiance as well as some light getting through because we weren't at totality. And even at totality, you would still have some amount of irradiance. So the key conclusions to this is that DARWin dual creates a streamlined approach to operating two different instruments at the same time. It allows for functionality with automating your sampling process. So we'll be able to take scans at 5-minute or any increment of time that you deem is good for your experiment. So it's very painless for the scientist. The only thing that we really needed to adjust was the Gershun tube in order to ensure that it's targeting the sun appropriately and not missing the sun as it moves. There's different equipment that you can use to actually track the sun and not need to change the Gershun tube, but there's functionality with being able to remotely operate the instrument. There's functionality being able to operate two instruments at the same time, as well as these accessories that give you the ability to just measure the energy, the direct energy from the sun, like the Gershun tube or 180-degree field of view using the inline diffuser. So this advancement with the DARWin dual adds a lot to different scientific approaches and will allow for better environmental and energy research in the future. So thank you very much. And I'm happy to answer any questions that you have regarding this experiment or our instruments as a whole or any applications. Thank you.